Good morning, students. In today's lecture, under this NP Hard and NP Complete, I will tell you about the vertex cover problem, and I will show that vertex cover is also NP complete problem. In our previous lecture, we have covered all these problems: circuit SAT, CNF SAT, 3 SAT, and then I had reduced clique problem from this CNF SAT. Now in this lecture, I will prove that this is NP complete, and for that I'll reduce clique problem to vertex cover problem. So first this is just the revision of what we have done previously, that what is the clique problem. I'll just tell you that. What was a clique? Suppose if this graph is given to you, we need to find out, is there any subgraph of this graph that is complete? Yes, like this. 1, 2, 3, 4. This is the subgraph of this graph, and that is a complete graph. Complete means every node is connected to every other node. So this graph is having a clique of size 4. And what was the clique decision problem? Clique decision problem was that, suppose if a graph is given to you, you need to find out, is it having a clique of size k? If it is yes, then you can say it is having a clique of size k, otherwise not. So this was the clique problem. Now first I will tell you that what is the vertex cover problem, and then I will reduce the clique to vertex cover problem. So first thing is that what do you mean by vertex cover of a graph? Okay, now suppose this graph is given to you. We need to find out the vertex cover. Now vertex cover means you need to find out those vertices that cover all the edges of your graph. That means that touch every edge in your graph. Suppose like here, this graph is given to you, and suppose if I'm taking the vertices 2, 5 and 4, we'll see whether these vertices cover all the edges of your graph. Okay, for this, suppose I'm first taking 2. I'm taking this 2 vertex. Okay, now what are the different edges that are that are starting from this 2 node? So this edge, I'm cutting this one, I'm cutting this one, and I will cut this one. So this 2 node is covering, like you can say, it is covering these 3 edges. Okay, next you take the node number 5. Suppose I'm taking this one now. Now again cut all the edges that are touching 5 node. Okay, which edges are there? This 5, 1, 5, 3 and 5, 4. Okay, so these two vertices 2 and 5 will touch all these, or you can say will cover these 6 edges, but still one edge is more. For that I need to take either 3 node or the 4th node. Suppose I have taken the 4th node, so you can say this is also going to cover this edge. Is there any remaining edge over here? No. So you can say these 3 vertices are covering all the edges of our graph. So that is the vertex cover of a graph, VC. Okay, so now what is the definition of this? A vertex cover of a graph G is equal to VE is a subset VC. So this vertex cover, that is a subset of V. What is V? V contains all the vertices 1, 2, 3, 4, 5. So it should be firstly a subset of this, such that if AB belongs to E, like if AB, like if 1, 2 is an edge, 1, 2 belongs to E, then either A should belong to this VC or B should belong to BC, or it can be both. Suppose I'm taking 2, 4, 2, 1 first. So 2, 1 is an edge. AB is an edge that belongs to E. Yes, 1, 2 is an edge. Then either 1 should belong to VC, but here 1 is not there, or 2 should belong to VC. Yes, 2 is here. Okay, or you take this 2, 4 edge. 2, 4 is an edge over here. Yes, then either 2 should belong to this VC. Yes, 2 is here, or 4 should belong to this, or both. So actually here both 2 as well as 4 are here. So that is the definition of your vertex cover. Now what is the size of the vertex cover over here? There is a vertex cover of size 3. Okay, so vertices in VC will cover all the edges of G. Now we have to prove that vertex cover is NP complete problem. Now in order to prove that any problem is NP complete, what was the first condition? We need to find out that is it a decision problem? That means like we need to put this problem in such a way that the output of that should be either yes or no. Like here I have written over here, like you can say, suppose a graph is given to you, you can ask the question, is there any vertex cover of size k? If answer is yes, then it is having that vertex cover, otherwise answer would be no. Like for this graph, I can say, I can ask you, is there any vertex cover of size 2? No. Is there any vertex cover of size 3? Yes. Okay. So vertex cover takes a graph G and integer k as input and asks, is there any vertex cover of G which contains k vertices or not? If it is there, answer would be yes. Otherwise, answer would be no. So this is the definition of vertex cover, and according to the first condition, I have shown you that vertex cover is a decision problem. Okay, the next condition that we need to show is that vertex cover should be NP problem. Now again, what is NP? NP means, is there any non-deterministic algorithm that can be solved in polynomial time? Okay, for that I have written this non-deterministic algorithm, like you can say it can be solved in polynomial time. Now given VC, the vertex cover of G, for each vertex that belongs to VC, remove all the incident edges. Like here, what we have done previously, what they are saying, like suppose a vertex cover is given to you, 254. Okay. Now for each vertex that belongs to VC, cut all the incident edges. Okay. So again, I'm taking this. For vertex cover 2, cut all the incident edges, that is cut this one and cut this one that are starting from 2. Then for 5, cut all the incident edges, this, this and this one. For 4, cut all the incident edges, this one. Then you will check, is there any remaining edge in the graph? Is there any remaining edge? No. Okay, if it is no, that means it is having a vertex cover of size k. But suppose if there is any remaining edge, then it is not having any vertex cover of size k. Now this can be done in polynomial time. Okay, why? Because your non-deterministic algorithm would take all these vertices in parallel and it will cut all the incident edges in parallel. Okay, so this problem can be solved in polynomial time but by using non-deterministic algorithm. Okay, so again I'm repeating, for each vertex that belongs to VC, remove all the incident edges. Check if all the edges are removed. Yes, like in our case it was removed, so you can say that it is having a vertex cover of size k. Now this problem can be solved in big O of number of edges plus number of vertices. Okay, so it is polynomial in time. So this vertex cover belongs to NP. That means this problem is in NP. Now the third one, that is like it will be difficult one. Like we have to show that vertex cover is NP hard problem. So in order to show that vertex cover is NP hard, we need to reduce a problem that is already proved to be NP hard, and we will reduce that to vertex cover. Now here what I have taken a clique problem. Okay, now that clique problem will be reduced to vertex cover problem in polynomial time. If I am able to do this thing, then I can say that the vertex cover is NP hard, as I have already shown you that clique problem is NP hard problem. Okay, for that I need to take a graph GVE. Suppose here I'm giving a graph G and I'm giving the K as the input. That means I'm saying that graph is having a clique of size K. So that is the input that I'm taking. Okay. Now that graph will be having a maximum clique of size K if and only if. Now here I have written G dash. If G dash, I will tell you what is that. G dash is a complement of this graph G. If and only if the graph G dash has a vertex cover of size number of vertices minus clique. That means if G dash is having a vertex cover of size this, then only your input graph will be having a clique of size K. Otherwise, it is not possible. So if I'm able to reduce this problem to this, I need to show this thing. So first thing is that I will tell you that what is G dash. That means complement of a graph. Now here you take this graph in which you are having 1, 2, 3, 4, 5 vertices. So G is B, E. E is these edges 1, 2, 3, 4, 5, 6 and 7 edges are there. Now what would be the complement of this? Complement of this graph is this. That means you assume that this graph is your complete graph. Okay, let me make this thing. Okay, now if you want this graph to be complete graph, there should be an edge from 1 to 5, from 1 to 2 and from 1 to 4, because in a complete graph you should have an edge between all the nodes. So there was no edge between 5 and 1, 5 and 2, 5 and 4. So I have made these. So you just consider these red lines and make this graph again. 5, 1, 5, 2 and 5, 4. So that is the complement G dash. In that vertices are same V. Set of vertices is same, but E dash is what? That is 5, 1, 5, 2 and 5, 4. But here the E was 1, 2, 1, 3, 3, 4, 4, 2, all these edges and 3, 5. So if you will combine this graph and this graph, means without these red lines, the previous graph, original graph and this graph, you will be getting this graph. So what is that? That is a complete graph actually. Okay. So if you are merging the graph G and G dash, you are getting a graph that is a complete graph, similar to this one. Okay. So this is the complement of a graph G dash. So like what was our problem? Our problem was this is the input. We are giving a graph G in which the number of vertices are n. How many vertices are there? 5 and clique is k. Now what is the clique of this? What is a clique? Again I am repeating. Clique is a subgraph of this graph that is complete. Now this is the subgraph of this graph that is complete. This subgraph that is complete one without this 5. 1, 2, 3, 4. So what is the size of the clique over here? Clique is 4 for this graph. So you are giving a graph with clique of size k, and I need to find out is G dash is having a vertex cover of size V minus k. If it is possible, then that means we have reduced this to this in polynomial time. Like you take this graph, I have made G dash. Okay. Now just find out that what is the vertex cover of this. Vertex cover means you need to find out the number of vertices that covering all the edges of this graph. Okay. Now vertex of cover of this graph is just 5. 5. Why? Because if I will take 5, 5 1 will be cut, 5 2 will be cut and 5 4 will be cut. Is there any more edge over here? No. So I can say the vertex cover of this is what? 5, only 5. That means that is your 1. So vertex cover of this graph is given by number of vertices, that is 5, and minus clique size. And what was the clique size of this graph? 4. So 5 minus 4 is 1. So you are getting that. So if we are giving a graph with number of vertices 5 and clique size 4, then G dash should have a vertex cover of size 5 minus 4, 1. So I'm able to get this thing. So you can see that this problem is being reduced to vertex cover problem. And one thing more here, what is a vertex cover of this? This is the size. Size of the vertex cover is V minus K, but what is the vertex cover? Vertex cover is given by this, like you can write down vertex cover is given by V minus V dash. Like for this graph, what is the V? V is set of vertices 1, 2, 3, 4, 5. And what is V dash? V dash means like here, what is the vertices that are in the clique? V dash is that thing, the vertices that belong to clique. Like what is here clique? Clique was 1, 2, 3, 4. So I can write down clique is 1, 2, 3, 4. So if you will find out V minus V dash means V minus V dash, that means you don't have to take those elements that are already present in V. So I won't take 1, 2, 3 and 4. So what is remaining? 5. So you are getting 5. So you can say that the vertex cover of this is 5. Size of this vertex cover is given by number of vertices minus k, and the vertex cover, like what are the set, what is that set? That is given by v minus v dash, where v dash is a set of vertices that belongs to clique. So here you can say that. Now I have shown you that vertex cover is a decision problem. It is in NP and it is NP complete problem. Okay, so it is NP hard, so I can say it is NP complete problem. Okay, so I have used this one clique problem to reduce this to vertex cover problem. So this also I have added in this graph, in this reduction graph, NP reduction graph. So again I am repeating, what is a vertex cover problem? If you have been given a graph G and an integer k, you need to find out, is there any vertex cover of size k? If you are having the vertex cover of size k, the output of this would be 1, otherwise it would be 0.